Hello students, welcome to the 18th lecture on particle physics. And in the last lecture, we had started the discussion on charge conjugation operation, and today we shall continue with that. We were talking about fermion, anti-fermion bound system like positronium system or quarkonium system. The simplest quarkonium system that we can think of is pi plus u d bar or pi minus, that is u bar d, or positronium system is e minus e plus. What we discussed that when we talk about charge conjugation operation on quark anti-quark pair, then since we have quark anti-quark pair, charge conjugation will make it q bar q, and that is equivalent to the reflection, and this we take into account for the bound system the orbital parity to be minus 1 to the power L. And we have two fermions, those are described by anti-symmetric wave function, and overall symmetry of the two fermions. Yesterday we have seen that we should take a factor of minus 1 to the power s plus 1. Therefore, there should be a factor of minus 1 to the power s plus 1. There should be a factor of minus 1 to the power L. And then, to be consistent with Dirac theory and in quantum field theory, we need a factor of minus 1. Therefore, overall, if you include all these three multiplicative factors, we have for quark anti-quark system a factor of minus 1 to the power L plus S when we use charge conjugation operation. Now, if I'm talking about a positronium system, which is an electron-positron bound system, the Coulombic potential is given by minus 1 by 4 pi epsilon naught E squared by R, and the energy is given by minus 13.6 electron volt by twice n squared. This we have discussed in the last lecture. Now, the 3s1 state with principal quantum number n equal to 1 is called the orthopositronium state, and the 1s0 state is called the parapositronium state. And the tables in following table, we are going to show the positronium state with the principal quantum number n equal to 1 and n equal to 2, along with the total angular momentum J, parity P, and C parity. As you can notice that if I have S state which corresponds to L, minus 1 to the power L plus S. L is 0, therefore we have simply minus 1 to the power S. S can be for the two fermions of spin half, S can be 0 or S spin can be 1. And this, if S is 0, then this is even parity state. If S is 1, this is an odd parity state. Now, if the system is in P state, then for S equal to 0, this will be an odd parity C state, and this will be an even parity C state, and similarly for the D state, for which L is equal to 2. Now, if we are talking about the positronium system with n equal to 1, L equal to 0 or L equal to 1, because with n equal to 1 we can get L equal to 0 or L equal to 1. The state, atomic state, is represented by general nomenclature is it is represented by twice S plus 1 Lj. Now you notice L is 0, which is representing a S state. Therefore, this is my S state. And then for S is equal to 0, this is 1 S, and L is 0, S is 0, this is 1s0. This is what I have represented it here. Then L is 0, S is 0, your J is 0. while parity is minus 1 to the power L, and C-parity is minus 1 to the power L plus S. Therefore, what you are getting, that your L is 0 and S is 0, this is minus 1 to the power 0, and that is even. Now, when your L is 1, notice when your L is 1, then what is happening? You have N is still 1, and you are getting C is equal to minus 1 because L is your 1, your S is 0. This is giving you L equal to 1, and then you are getting it to be odd. So this is how the different positronium states you can get, that will have a definite spin, that will have a definite parity, and that will have a definite C parity. Similarly, if we go to quarkonium system, where we have a CC bar bound state or where we have BB bar bound state, then in this case where we have CC bar bound state or BB bar bound state, this is similar to electron positron bond state. And as you can see that when N is 0, you can have S is equal to 0 or S is equal to 1. If S is equal to 0, you have 1. S is equal to 1, you have 3. Since we are talking about L equal to 0 only, because with N equal to 1, you can get L equal to 0 only. Therefore, you have S state and your S is 0 in the first case, this case, and L is 0, which your J is 0. Therefore, your J is 0. Then you are talking about parity, and then you are talking about C parity. Therefore, you can see that like in the previous case, we have a factor of minus 1 to the power L for L plus S plus for the C parity. Therefore, S is 0 and L is 0. That is giving us C eigenstate to be positive. That means that has got positive C parity state, and it has been observed in nature that there exists a particle eta C, that means this contains a charm anti-charm with approximately center of mass corresponding to a center of mass of energy 2984 MeV. These energies are in MeVs. And you have a BB bar state with the energy 9398. Therefore, you have charm anti-charm state as well as you have bottom anti-bottom state. Similarly, if you talk about S is equal to 1, still your L is equal to 0. That means your J is equal to 1. And then using this minus 1 to the power L plus S, you see that this is 1, this is odd. Similarly, you have obtained parity. You have J by psi meson, which peaks at the center of mass energy 3097 MeV, and you have another epsilon meson with a quark configuration of BB bar at center of mass energy of 9460 MeV. Now, similarly, you go ahead, you talk about L equal to 1, S is equal to 0. You talk about L equal to 1 and S is equal to 1. When your L is 1 and S is 1, your possible J will be 0, 1 and 2. And that is why you can see that when I am talking here about L equal to 1 and S is equal to 1, then we have 0, 1 as well as 2. While when L is 1 and S is 0, we have only one possibility, that my J is equal to 1. Therefore, if you talk about principal quantum number N, this principal quantum number N will have L equal to 0, while principal quantum number N equal to 2 you can have L equal to 0 as well as L equal to 1, and then just as you do in the atomic theory, you are forming the different atomic state, or you can call it quarkonium state, and these quarkonium states have different angular momentum, they have different parity, they have different C-parity. Therefore, in general, when you will look at the books, what they represent a state corresponding to J equal to 0 and parity odd and C-parity to be even, they write it as 0 minus plus, where the first minus sign stands for parity and the second plus sign stands for the C-parity. Therefore, if I am writing it as 0 minus plus, that I am talking about this state. Similarly, here if I take this example, 3p2, this will be represented by 2 plus, the state will be represented by 2 plus plus. 2 plus plus charmonium state which correspond to chi C2 3556 and bottomonium will correspond to chi B2 9912. Therefore, when we talk about parity and C-parity for the different bound system, these different bound systems, they define the states, and corresponding to that you get different observed particles. Therefore, if you recall, when I was talking about mu plus mu minus going to give you a set of mesonic states, we drew something like this. The different resonances correspond to the different particles, and these are the particles which I have tabulated in this table. Therefore, and this you see that since nobody has found out separate quark or anti-quark, or you have never found out an isolated quark, therefore you keep on pumping energy to the system, you will get somewhere some resonant states. But mind it, these resonant states are not equally spaced in energy, as you can find out that one is at 2984 center of mass energy, another is at 3097, but this first and second difference in center of mass energy is different from the second and third, and that is different from the third and fourth, and so on. Therefore, you cannot exactly predict that my next resonance will lie at this center of mass energy. But as you will go down this line, there are chances that you will get some resonance, and then when you have got that resonance, that will correspond to some particle, and if you are naming that particle will have certain angular momentum, certain C-parity, and certain parity. So this is how people have observed the different quarkonium states in nature. Here, for example, I am showing it on the left hand side for the charmonium state and on the right hand side for the bottomonium states, and as you can see that there are various mesons which consist of C bar, and on the right hand side they consist of BB bar, and as you can notice that we have here, since I am writing it as 2.98, that means if you look at the previous example, that was 2984 in MeVs. Here I am talking about 2.98 in GeVs. Therefore, this resonance corresponds to a center mass energy of 2.98 JeV. You see, in the previous case, we had 1s0, we had 0 minus plus. Come to this 1s0, 0 minus plus, we have one resonance. Similarly, the other resonance, and so on. And as you can see here also, if you look back, we had 9398 MeV. Now, this will correspond to 9 approximately 4 JeV, and we have 1 eta beauty meson, which consists of BB bar, and you see this has angular momentum 0, parity odd, and C-parity even. So this is how one determines the properties of the particles and the different meson, anti-meson, or BB bar state or CC bar states. And this can keep on going because till now nobody has seen an isolated quark. Now let me go to charge conjugation violation and talk about charge conjugation violation in weak interactions. Now, we have seen that yesterday in the day before yesterday's lecture that helicity is defined as the projection of a spin of the particle in the direction of the momentum of the particle. And this is what I define helicity as this, that projection of a spin in the direction of the momentum of the particle. And this we wrote something like this, and this was defined by the following values: plus 1 or minus 1, which we call it as the spin and momentum. If they are in the same direction, this we will call it as right-handed helicity state, and minus 1, then spin and momentum are in the opposite direction. This is the left-handed helicity state. We discussed in the class that for massless particle, the particle will have definite helicity, but for massive particle, it won't have. It will have both left-handed and right-handed helicities. Now, since we are talking about neutrinos, and neutrinos are left-handed particles, therefore the momentum of the neutrino will be directed opposite to the direction of a spin, while for the right-handed neutrino, the momentum of the neutrino will be along the direction of the spin of the anti-neutrino. Now let us do the C operation. Now, what does this C do? This C takes a particle to an anti-particle state. Therefore, nu will become nu bar without changing its momentum, without changing its position, without changing time, without changing its spin, etc., etc. Therefore, as you can see, when I am operating by C, this nu is becoming nu bar, and then momentum is unchanged as well as spin unchanged. But since this is becoming anti-neutrino, this was a left-handed neutrino, this has also become a left-handed anti-neutrino. While similarly, if we talk about a right-handed neutrino, which has been observed, this is anti-neutrino, spin and momenta, they are projected along the same direction. When we are doing the C operation, then anti-neutrino is becoming neutrino, and as you can see that this neutrino is right-handed. But we know that left-handed anti-neutrino and right-handed neutrino have never been observed. Therefore, C is not a good quantum number in weak interaction, while it's good quantum number in electromagnetic and strong interactions. Therefore, C operator is transforming a left-handed neutrino to left-handed anti-neutrino, and here a right-handed anti-neutrino to right-handed neutrino, which have not been observed, and C gets violated in the weak interaction. Now I am going to demonstrate or tell you about a very beautiful experiment, which is tabletop experiment, and much thought has gone before performing this experiment. This is famous Goldhaber experiment to determine the helicity of the neutrino. And as you know, neutrinos are weakly interacting particle. Therefore, nobody ever observes a neutrino. What they observe is a final state. Here also, we are going to talk about neutrinos and its helicity to be left-handed without observing the neutrino. what we will observe is the polarization of photon, and the polarization of photon will determine the helicity of the neutrino. Therefore, this is an important experiment from which we concluded that neutrinos are left-handed and antineutrinos are right-handed. Now, I'm talking about the thoughts those have gone before performing this experiment. See, what was done? First, a nucleus was thought to have a spin angular momentum equal to 0. They thought that we should try and find out a nucleus with angular momentum 0 while the nucleus is in the ground state. Now, this nucleus captures an electron, resulting into an excited nuclear state, plus a neutrino is released to conserve electron-lepton number. Now, this excited nuclear state, people took that nucleus which goes from angular momentum 0 state to another nucleus which is in excited state having angular momentum 1, and then that excited nucleus decays to or goes down to the ground state, which is a spin 0 state again, by transforming its angular momenta to the emitted photon. Therefore, this experiment is very interesting. What we are talking about, a nucleus first in the ground state having angular momentum 0, which absorbs an electron, goes into another nucleus which is an excited state, which is an angular momentum 1 state, and a neutrino gets emitted. Now, this excited nucleus, by emitting a photon, goes down to ground state with angular momentum j equal to 0, and this emits a photon, and the angular momentum of the photon is carried by this angular momentum of the nucleus is carried by this photon. Therefore, you can see that I'm talking about an electron which is a spin half particle. We are talking about a target which is europium, which has angular momentum equal to 0. And what is happening? That samarium star is getting formed, which is an unstable nucleus. It has angular momentum equal to 1. Besides that, a neutrino is emitted to conserve electron-lepton number, and we know that neutrino is a spin half particle. Now, this samarium goes down to ground state by emitting a photon, and this ground state is an angular momentum 0 state, and the photon is carrying that angular momentum, and neutrino was emitted as we have discussed. Therefore, what you will realize that when it is getting absorbed, and these samarium star and neutrino, to conserve momentum, they will go in opposite direction. And when they will go into opposite direction to conserve momentum, they have to also conserve the angular momentum, because both linear momentum and angular momentum, they are exact conservation laws, and therefore what you are talking about, j is equal to half, here j is equal to 0, therefore the total initial angular momentum should be half. Now look at the final scenario. This is 0, or if you take this j is equal to 1 and j is equal to half, this means that to get half, they should be direct, this angular momentum should be directed in the opposite direction. This opposite direction can be like this, scenario 2, or this opposite direction can be scenario 1. Therefore, to conserve linear momentum, samarium star and neutrino, they have to be emitted exactly in the opposite direction. And to conserve angular momentum also, they should be emitted exactly in the opposite direction. Therefore, what you notice that if you talk about the helicity of the neutrino, then here momentum and spin, they are in the same direction. Here momentum and spin are in the opposite direction. Therefore, this is a right-handed case and this is a left-handed case. Up to this point, everything is fine. Now you see what I am telling you, that this samarium star is emitting a photon. It is moving ahead. It's like this samarium star is going like this. In the meantime, it is emitting. It is going to ground state by emitting a photon. Now, if it is emitting a photon, the photon will move in the forward direction and it will keep the direction of samarium star and to conserve momentum, and it will take the angular momentum of the photon. Therefore, in the second case, that means this samarium star, when it is giving or releasing a photon to come to the ground state, is carrying the spin of the photon and it is carrying the same direction as the direction of the samarium star. Therefore, notice that the direction of momentum of photon, the emitted real photon, is opposite to the direction of linear momentum of the neutrino, as well as their angular momentum also are in the opposite direction. But by doing that, what you can see that the helicity of neutrino, nu e, momentum and spin, if in the scenario 1 is right-handed, the same is true for the photon also. Its momentum and spin are in the same direction. And in the second scenario, if momentum and spin of the neutrino is in the opposite direction, they are in the opposite direction, then the momentum and spin of the emitted photon, that would be also in the opposite direction. That means there is no need to determine the helicity of the neutrino. If we determine the polarization of the photon, we will be able to tell that what will be the helicity of the neutrino. This is what was done, that since from angular momentum conservation, we took the example where we had the linear momentum and angular momentum in the same direction. Here in the first case, that was resulting to us a right-handed neutrino or photon. The same scenario in the second case, we have a left-handed neutrino and left-handed photon. Now that means we have to do nothing. We have to determine the polarization of the photon, and from here we will determine the helicity of the neutrino. We shall stop here, and from this point we will again start our discussion that how helicity of the neutrino was determined by Goldhaber. Thank you.